So sad. Okay. Well, beast. All right. Alrighty. Let's go. It's a very exciting day. It's always an exciting day. Okay, Matrixology. This is number 13. We are getting somewhere. I know you're feeling the joy. We're getting somewhere. We're going to talk a little bit more about row space. And then, if you want to join the NSA, for example, this is going to help. Okay, so final frontier, left null space, whatever this thing is. I need to control myself. Okay, so, and we'll have this very nice aspect of the subspaces of an orthogonality piece. We've seen a little bit of it. Things that are at right angles are good. They don't share anything. They're nicely separated. We will get to the fundamental theorem of matrixology, which is that calculus is just not good. No, it's actually about linear algebra. All right, so, and in fact, we get most of it. We have to spend another 6 weeks to get a little bit more. Right. The big picture thing, which I know is nicely confusing, we're going to deconfuse that slowly, and we're going to have a new matrix to play with. We still have Physic. And Inigo, but we also will have this guy, Vizzini. All right. Okay. Vizzini is very small, not very smart. Okay? Dunning-Kruger situation. All right. All right. I'm going to talk about the Princess Bride. I could move to other things, but, you know. Okay, so you can see we have the grades are up. If you haven't got your assignment, you can get it after this performance here. And the solution's right. Solution's being passed around. Okay, but you can see where things are going for you here. Right. All right. It's good. I think that's all. I have a request to get rid of this object. So we'll do that. Good. It's painfully slow. It's like the same way the good guy gets lowered into the lava pit and escapes in the movie. All right. Okay, hilarious. All right, so row space, wooden spoon. So let me just recap a little bit. Row space was this very simple thing. It's just what's the linear combination of the rows of your matrix A. And amazingly, we'd done everything for this. Everything was done. Okay, so a little recap. Our big deals are still here. They've been slowly erased. Row space. So this is, and we have an excellent question, is what are we going to call this thing? We will get to it very soon. Okay, so we don't have a nice little, right? We say C of A for column space and N of A for null space. We don't have one here. But enlightenment is coming. Okay, so this is the linear, so it's all linear combinations of the rows of A. The rows of A. Right? And it's sort of so there's this. It's a kind of it's a partner in crime of, and we'll see this for this little Vizzini character, for the column space of A. These things match up. Its dimension is equal to R, the rank of the matrix, rank of A. Same as that for CA. We didn't get through all the big deals, so I'll just list them. A basis for row space. It's all the non-zero lines in the non-zero rows. This is awesome. It's great. The non-zero rows in RA. And this is already done. Right? Already done. Right? So we've been finding this reduced row echelon form all along. What other minor lies have I told you? Okay. It's true. It's where the solution, where the particular solution, the thing we've been calling xp lives. Right? And that's from this equation, a times x equals b, this silly thing we've distilled into, a times xp plus xh. This is homogeneous. Let me write down here, this is homogeneous. That's an, yep, homogeneous. I will miss chalk, actually. P is particular. Let's do it. P is particular. Right, A times X particular. If there is a solution, right? If solution exists, it has this form in general. A times XP, that's the bit that equals P. B, this is B. I'm not really crossing out, that's B. And then A times X homogeneous equals 0. 0. This is 0. So the whole thing equals B. Solution exists when? B is what? B is in a particular place. Column space? Yeah, good. Right? This is B is in the column space of A. All right. Okay, so there, we'll use these examples, Vizzini and Inigo, maybe not Fezzik. Fezzik is very big, big friendly French matrix. And I'll give you explicit examples of this. Okay. This was good. So these are just recaps. So we've got our brains back in order. So any vector, who wrote this? Any vector in the row space of A is orthogonal. Let's use other words. Orthogonal. What's another good word? Orthogonal. Perpendicular. Which is a very silly name. And our mathematical symbol is this. Right? All of these things, whichever one you want. Perpendicular to. So any vector in row space is perpendicular to any vector in null space of A. Right, good. Right? So, just to add, this is sort of out of order, I suppose, but row space and null space, these are subsets of Rn, right? This is where the X lives. And the dimension of these things add up, right? So the dimension of row space equals R. And the dimension of null space, so much awesomeness, equals N minus R. We can add these things together. They add together very suspiciously to give N, the dimension of this character. Okay. Whoop, that character. All right. That's recap time. Okay. Pretty good. We've got that. I guess I've said it here. Linear combinations of rows of A. A basis for row space is the non-zero rows in A. Well, let's write it like this. So this is important. The column space of A is not equal to, in general, this is in general. Let me say it again. The column space of the reduced row echelon form of A, right? We destroy the columns. We don't, but the relationships stay the same. Very important point. But the row space of A equals the row space of the reduced row echelon form of RA. Right, we're just adding and subtracting combinations of rows. We're messing around, and this is a really nice, clean story down here. We clean out all the pivot columns. We end up with some very nice vectors. All right. let me keep going with this, and we'll get some examples out from these matrices, and hopefully things will start to click, right? We've had to slowly get into this, but there are lots and lots of pieces that after we've got it in your heads, you can say, oh, this is true, and then this is true, and this is true, right? All right. It's an aha moment kind of thing. Might take a while. Okay. All right, so this is all right, so we had this good question. What are we going to call this thing? So big deal, maybe number 8-ish? 7, all right, good. So let's say let's go back to Inigo, right? And we had A equals 1, 2, 2, 4, 1, 2. So A transpose, so we observe the following goodness. A transpose is equal to 1, 2, 1, 2, 4, 2, right? It's a simple transpose thing. We just flip it across the leading diagonal, which in principle just keeps going down. Flip. There it is again. Good, good, good. Simple operation. So the rows become the columns become the rows. So what can we say about the column space of A transpose? The column space of A transpose. Right, so column space of A transpose is every combination of these two. Yes. And seen. No, it's great. It's really, this is fantastic. This is fantastic. Right, we see this. Very simple. It's just what the transpose does. It changes columns into rows and rows into columns. Right, so rows to columns. So this is what we'll use for our notation. Because we've seen this kind of higher story, so instead of writing row space, an R for row space, and we've got an R already, it'd be a mess. We've got a big R, a little r, we've got an R with a, right? We've already got this one, and this one. What do you, it's bad. Okay, so we'll write row space, the row space of A as the column space of A transpose. And there's going to be this back and forth business of A transpose. Right? C, A transpose. That's it. So you have to, it is a C, it is for column, but you have to think, okay, column space, but it's a transpose, so we're talking about rows of A. Columns of A transpose, rows of A. And so here it is, right? So every linear combination of these two columns, they're 1, 2, 1, and it's 2 times 1, 2, 1. It's a very simple matrix. Every combination of these characters can be boiled down to some multiple of 1, 2, 1, and that's exactly what we have for the rows. Exciting? Okay. All right, so it will turn out soon that if we, and where should I should put it here now. Yeah, that's what that little thing says. Okay, all right. There's an asterisk and then a thing. Okay. Not an asterisk, different thing. Okay. Okay, so because of this, all right, so big deal number 7. How we doing? Yeah. 7 plus 1, yes. Oh my God. Well, I learned to do multiplication with sticks, actually. Okay, so let's see. So maybe it was pretty good. Okay, so because we've made this observation, row space of A is just the column space of A transpose. We can find a basis for the column space of A, sort of going back the other way, right? So find a basis. So this is a third way. And I'll recap the others at the end. This is a third way of doing this by finding the reduced row echelon form. Reduced row echelon form. This is very exciting. Really good. Echelon form of A transpose. And it's okay to be emotional about this. It's really all right. Okay. So that's really nice, because we did this kind of funny business where we said, well, let's set up AX equals B, and we'll make B B1, B2, B3, or whatever. And we'll do row reduction, and we'll get some constraints on the B's, and then we'll mess around with that a little bit, and that'll tell us what column space is. And I'll write this down in a second. And the second approach was to say, let's find the, it's a big observation. You find the column, the pivot columns, right? You find the pivot columns from the reduced row echelon form of A, and then you go back to A and say those columns are a basis for the column space of A. But this is even better. This is really clean. This is really clean. So we're going to call it, and I'm going to call it this. This is sort of a notation thing that's not in the book, but I think it's useful. So it's the reduced row, R, this R with this blackboardy thing that I do, is going to be the reduced row echelon form of blob, right? So it could be R of an apple matrix, for example, whatever it is. Then whatever blob is here, we want the reduced row echelon form of that. And that's, we have a principled way of doing that. Yeah, all right, let me okay, let's have previously, right? Which should be said in a deep voice. So previously we had, right, we did this. So for instance, we found column space of A, I mean, it's a bit elaborate. We end up with a basis. We found a column space of A by solving this. So it's a bit of a pain, actually. So it's this sort of thing. 1, 2, 2, 4, 1, 2, B1, B2. This sort of thing, right? This is very quick, so we can do it. In this case, it's just 1, 2, 1, 0, 0, 0. Let me get it wrong. B1, B2, minus 2B1. And so we have a constraint here. First equation doesn't tell us anything. The second equation, row 2, says 0 equals, that's a colon, B2 minus 2B1. Right? Just very quickly, we can do it. All right? So we'd say, OK, B has to equal B1, B2. And we have a constraint here. We can say B2 is 2B1, B1, 2B1. Right? Stick this in here. And then it's B1 times 1, 2. Now that's all of column space, because we're going to say B1 is an element of real numbers. There's no constraint on B1. And then we can kind of easily see that this is a basis here. We had an argument for why if we end up with 30 of these things, you know, B1 times something and B7 times something and whatever it is, we would still have we could get a basis out of it. So we're finding column space entirely. So that was, this is, let's call it 1. And then there was 2. And I'll just say what it was. So we find the pivot columns. This is more elaborate for sure. Pivot columns in the reduced row echelon form of A. And then we saw painfully, absolutely, right? Painfully, with some thinking, you have to go back onto it, that the same columns in A form a basis for column space of A. Basis for column space of A. Right, so the pivot column here it is. Chalk, tray. Okay. Pivot, free, free. One pivot column, right? Go back here, here's your basis. Done. All right, and we had an argument for why that is. And we have to we'd have to go back through that. But this is a little ugly, this first one. It was an understanding one, though. We had to do this because it's like, which Bs can we make? Which music can you make from these instruments? This one, more subtle, a little more power. And then, so have we done it? I mean, so this should be clear, right? I mean, if we can find a basis for the row space of A by doing row reduction. An argument that we had over here, basis for the row space of the non-zero rows in the reduced row echelon form of A. So if we just flip the thing, right? We just flip the thing to A transpose, do row reduction, we'll have a basis for the row space of A transpose, which is the same as the color space of A. Yeah. Yes. Yes. So here it is. There's a basis for row space. Yes. Yes. And so let's do this example. I'm going to take a picture. Good. That's exactly right. So that is 0.4 over here. I brought a bigger camera because it works. I will put these up one day. I don't know. Possibly for my children. Okay. All right. Excellent question. So we okay? Am I okay? All right, I'm okay. So A transpose for Inigo is 1, 2, 1, 2, 4, 2. Right? Reduced row echelon form of this thing. What do we do? Right? So it's going to be, let's do it like this. We do our row reduction. R2 prime. We do, right? Everything is the same. All of those, right? The monks are not going to tell you to do a different kind of row reduction. There's a row 1 here. Minus something time, minus row 1. Right. Row 2 prime is row 2. Yep. And we can do the other one as well. Row 3 prime is row 3 minus row 1. It's not the monk's fault. It's mine. So that's 2 divided by 1 and 1 divided by 1. And you can just see what it is. It's fine. Yes, yes, yes. So 1, 2. So 2 of this one subtracted, 0, 0, 0, 0. And there is our reduced row echelon form. It has 1 pivot, 1 free variable. And so I'm going to write this as equal to, on this line, if that's okay, A transpose. Very, very important point. This is not equal to the transpose in general of the reduced row echelon form of A. In general. So you have to take A, find its row reduced form. You have to take A transpose, find its row reduced form, and then that will tell you everything about this matrix when it comes to this big picture story. There are always other hidden things. Sure. We all right? So that was a good. So is that okay too? Yeah. So don't do this. You have to do 2 row reduced forms. And this is 1, 2, right? So you have to read it off here. So the basis for the column space of A in this case, that should be a C and then a parenthesis, right? Is basis for we have to write out in words is 1, 2. Right? We turn the whole thing around, so now we have to turn it back the other way. Yes? I'll use some indelible chalk. Right, and we found that over here. We found it here. This was our first method for finding it. 1, 2. I know this is exciting. It's sitting here, 1, 2. It's our pivot column. 1, 2, 1, 2, 1, 2. And this is a beautiful foolproof method. Dangerously said that. Okay, but it's great. Okay, so this is great. This is the best way. Okay, I like it. So, and again, it uses everything you've done. You know about reduced row echelon forms. And we're just doing it to the transpose. And we're seeing it has this goodness. Okay, so that was from, it's over there. Shall I do Phasic? I'll do Phasic. Phasic is good. Right, it's A, and I'll just write down quickly, I won't do all the calculations, but this is a monster, a giant I should say, 4, 4, 12, matrices of unusual size, 4, 10, 18, and A transpose. You're just going to, you can write that down, right? Boom, boom, boom. 2, 2, 6, 4, 4, 12, 3, 6, 12, 4, 10, 18. And then we do row reduction, row reduce for leisure purposes. Right, you're having a great time, you love it, it's fun, and you'd get down to 1, 0, 2, 0, 1, 1. Yeah, 0, 0, 0, 0, 0, 0. It has this nice structure. It is rank 2. Right? It was a rank 2 matrix in general. We knew it was rank 2 from before. So it's rank 2, R equals 2. And so this is a basis, right? So the basis, you're going to squeeze it in here, equals the first one, 1, 0, 2. And then the next one is 0, 1, 1. Again, think about what we're doing. We can recreate all of these rows here. These rows can be recreated by some combination of these. Right, so the first one, let me show, I'll do that. Okay, so, right, that's the idea of a basis will create all of these rows and then everything those rows create as well. So you can see 1, 0, 2, 1, 0, 2. So we'd need 2 times this vector, plus 2 times this vector will give you the first one. Right? So the rows in the reduced row echelon form of A transpose, let's write it here. This is the reduced row echelon form of A transpose, can be used to rebuild, right? It's the same as the LU business, to rebuild all of the rows. I mean, it's a bit more than that. All of the rows in A transpose, and then everything they make. Everything they can make. Right, so these are the elemental instruments. These are elemental instruments. You can make these instruments out of them, and from that you can make every possible linear combination. But when you look at it like this, you think, oh, there are 4 rows, right? So that's sort of the dimension of this is 4, but it's actually really 2. So is that acceptable? Slightly disturbing? It's good. This is good. There was nothing new in that, sort of. That's pretty great. Okay, we went past the asterisk. There are lots of asterisks. Okay. Okay, so that's everything we need to know about row space. It's actually another column space. Is there fear and uncertainty and doubt that you want to clarify? Mm-hmm. No? I can help. Well, row reduction, so it's not, right, so it's not obvious to get to here. You do row reduction to unfold these. This is like getting U, as we did early on. And you can use those steps, which will be elimination matrices, to see how to go back. Right, so in a more elaborate thing, you could do it. This one I just used dubious observational, right? Yeah? So I'd have to think of, well, this one's the same. It's just 2 times that one. Okay. Actually, no, so you're done. You've got everything. You know there are 3 dimensions. These are 2 three-dimensional vectors. So you know that now you're in 3 dimensions. You have only 2 vectors in your basis. So it's a plane. It makes a plane. Yep. And they'll make a big, see how they have the identity structure always appears in these things. So you can't make one out of the other. This is really a basis. You can't eliminate one. The whole process strips away redundancy. Gone. Yeah. So really in here, I mean, look at this row. It's 2 times the first row. So there's some simple ones in here. So you can get rid of some of these things, and row reduction does that for you. It cleans everything out and distills it to a really simple basis. Not a perfect basis, but it's something you can see as a basis because it has an identity in here. There's a 0 here, can never make that 1. And that 0 can never make that 1. And otherwise it would be bigger identity structure. So, so you can see from here, it is a 2-dimensional subspace of 3 dimensions. 2 vectors in 3 dimensions. So somehow, and you add every combination of them, you get some plane. Okay, I'm just going to say, I also want to add that somehow this matrix here is somehow the square root of 30. It's true. It is the square root of 30, right. Yep. Yeah, okay, great, very good. So in the process of the way this is done, you always end up with 1s. Because we always divide out the pivots eventually. So you'll have a basis, and the first one will be 1, 0, 1, something, 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 right? It depends where the free variables are. The next one could be 0, 0, 1. It could be 0, right? Yeah, correct. So, right. So possible. So this is a very simple one, so they all turn out to be the same. But you're right. It could be 3, 6. It could be -2, -4. And a good basis, actually, for this would, in fact, be what's a really good basis for this, actually? You know it's any multiple of this. What's a nice basis? So we're allowed to multiply by any number we want. Let me just make this a little aside. Right? We found in all these different ways, and you're absolutely right. So basis for, so these are just notes. Okay, notes. Alpha, let's use an alpha. 1, 2, -3, -6, right? Apple and 2 apple, right? These are all good bases. Well, they're all bases. All bases all bases for the column space of Inigo Montoya. Right? What's a really good one? Almost. What would be nice to have? Integers are good. It's true. What do we do in, what's I hat and J hat and K hat got about them? There's something about those characters. They're all at right angles, and that's going to be a big deal. We don't have enough here to. Well, so we actually, because here's the subs, it's 1, 2, right? So 1, 2, so that's the subspace. It is this subspace. This is the column space of A is this thing here. It's all of those points. So you need to say this is the basis vector we have right now, 1 and 2. And so any multiple of that character will march us up and down. We can't split into 2. There's one special thing we could do to it. It has to point in that direction, but we could what is it? Well, with some, yes, which x though? Did someone say unit? Did you say unit? Unit vector, all right. This is a really good one. Put a root 5 out the front. Actually, root 5 appears in pretty good places. So it's unit length, right? This is Pythagoras, right? The length of this character here, 2 squared, 1 squared. 1 squared plus 2 squared equals the square root of 5. So if we divide by root 5, so this is unit length. So that's an expansion on your question, I think. Obviously an unnecessary. Writes down that never ask questions. Okay. Yes, okay, great. That was fantastic. So we'll get to this because we'll have to do this because if you have a basis, you don't want to put stuff into it. You want to be able to multiply the basis, the number you multiply it by. So when we have I hat and j hat, 7 times I hat and 8 times, the 7 and the 8 really mean things. If for some reason we made I hat length 4 and j hat length 2, we'd always have this kind of strangeness, right? We'd have to, yeah? And I know, yeah, well, we're used to the imperial system here, but this is a place where we have to do those things. I actually really like the imperial system. But anyway, good. It's very human. Let's see. So that's good. So let's go on to another horrible place. Okay, yes. Left null space. So why is it called left null space and why is it on the right? That is strange. So we've had null space and row space. They live in Rn, right? So far. And we're going to write them like this. So null space, row space. So I'll write them underneath. So null space, row space. These characters live in Rn, and we only have this one. It's a little sad. It doesn't have a friend. I mean, these two are friends. These two are friends. Right? They're both dimension R. That's dimension R for rank. And this is dimension, everyone knows, right? N minus R. Okay, so we could have another one. We could certainly have, so what about this one? What about the null space of A transpose? Why not? We could do that. So it would fit, right? Null space of A, column space of A transpose, right? So we swap these two the way we define them. So the other one over here would be null space of A transpose. So column space of A and the null space of A transpose must, just because we've constructed in this way here, they must, well, we haven't quite said this. Yeah, they live in Rm, right? They both live in Rm. And now we're thinking about, so there's this point, which is that A transpose times Y equals 0. This is the left null space equation. Left means sinister, right? Sinister. Yeah? Right? What? So Spanish, sinistra? Of course, the good old English just have sinistral, meaning evil. Yeah? Right. I'm not left-handed. All right, so gotta watch the film. Okay, so let's see. So this is the left null space, the left null space equation. I know I'm totally reaching for references. Okay, so left null space equation. What? Why is that called the left null space equation? And it's a Y because the Y's are different. This is what shape is this? This is a N by M, right? So Neptune by Mercury. At least we're keeping them the same thing. So this will be an M by 1, right? And then they match up, so this is an N by 1. As compared with A times X, different business. So Y left, and where is right? Where's the right one? Aha. Crazy monks. Crazy monks. Okay, so the monks were all right, because this is A. Here's our original one. Let's write down m by n, m by 1. And this is an m by 1. So the idea is, here's our A, and here's our x. Here's A, here's x. And that gives us this blob, m by 1. It's going to be like this. This is m by 1. This is what multiplies A on the right to give you 0. X is on the right. So we actually were looking at not the null space equation. X is on the right. So our basic null space equation, so null space equation, our beloved, you can write, I know you can put little hearts and things around. Our beloved is actually the right. The right. See, it's so built into the language. It's just really wrong. Right? It doesn't mean it's correct or good. It's the right. Okay. And why is this? But this is on the right as well. Yeah? So what is this madness? How is that thing actually on the left? How can we make that be on the left? Yes! All right. What? So we have A transpose Y equals 0. And so again, these are boxes, right? So this is n by m. Here, this is n by 1. And this is n by 1. So we take the transpose of both sides. And because it is right, correct, the correct thing to do, and also kind of awesome, what happens to this? Oh, yeah. Oh, I can actually. I thought, look at that. Thank you. I know you said the things. Right, good. And I know you want it to be, our brains want it to just go in here, but that's not true, right? So it's Y transpose, boom, and then A transpose transpose, and this is 0 transpose. So this, and this, of course, transpose transpose, is just A. So we're back to, that's a transpose there and a transpose there. So this looks like this kind of a thing. There's A, it's an m by n. And if you want to multiply by the left, on the left by a vector, it has to be a row vector. And this is 1 by m now. Good, right? And the whole thing ends up as a row vector. It's 1 by n. What is this multiplication? I know we've talked about different types of multiplication. It says basically, come over here, take the first row times whatever's here, the second row times whatever's here, stack all those rows together, and get this. It goes, right? The columns from the right says combine the columns with these weights. This says combine the rows with these weights. It goes, make that noise. This is a 0. Zeros. Important to make noises. Okay, let's see. Okay. How do you feel about that? That's pretty good, right? When we've done these things, it's just A transpose. It's just A transpose. So what's special about this little beast? And it's on the left. Let me say it here. On the left. Right? Good. So that's our left null space. And really our null space is the right null space. I'm having a good time. Yes. Okay. So let's find out some things about left null space. Well, I trip on myself. Right? So we get lots of things for free because of the monks. They're not evil monks. Some of them were. Okay. Okay. Let's see. Let's see. Okay. This is good. It's on the left. It's great. All right, so let's find out for our friend, our brave friend. Should I just pull this down and erase it? I guess so. Yeah. Is that all right? I'll leave that there. Let's find some left null spaces. Okay, great. I don't know if we'll get the Vicini. Oh, so much. Vicini, who is Sicilian, by the way. Let's see. Yes. Okay, so let us find a left null space. And then see what's going on with this thing. All right, so Inigo. All right, so we have A equals 1, 2, 2, 4, 1, 2. So we're solve A transpose Y equals 0. And so it's going to look like 1, 2, 1, 2, 4, 2 times Y1, Y2 equals, what am I doing? Yeah, 0, 0, 0. Good. Okay. So we're going to do row operations. This is going to be, we're going to rewrite this as 1, 2, 2, 4, 1, 2, 0, 0, 0. Right? Augmented matrix business. We did this row reduction earlier. There it is. Yes. Yes. So from before. And of course, these are all zeros, so we don't have to do anything special there. This is 1, 2, 0, 0, 0. And we get zeros here. This blob is, of course, the reduced row echelon form of A transpose, where A is Inigo. And it's a null space. Null space equations are very nice, right? There's always this sort of one way to deal with them. There's only one equation here. So equation 1 is y1 plus 2y2 equals 0. We have, you know, the sort of the flip side. This is a pivot. P for pivot. F for free. Right? So pivots in terms of the free express pivot variables in terms of the free. Same thing. Yes, yes, yes. Free ones. As always. Right? As always. Always do this. So it's y1 equals minus 2y2. That's all we have. And then we always go on to this next step. Of course, we're writing y's now because we're on a different side of A. y1, y2. Replace the pivots by their expressions. So this one gets replaced as minus 2y2. y2, we're doing the same stuff. We just have y's instead of x's. And so we can pull out we'll always pull out the free variables. If there are more than these, there'll be more vectors sitting here, but there's just where y2 is an element of the real numbers. Whoopsie. Yeah. So that should work, right? So this matrix times minus 2, 1. So minus 2 of the first column. It's a simple one. Minus 2 of the first column plus this one equals 0. Right? They're multiples. Yep. So we did the right thing. So the null space of A transpose, let's write out these things, is equal to all y equal to y2 times minus 2, 1. y2 is an element of the real numbers. Right? This is an infinite set, a basis for the null space. Left null space is just one vector. It's minus 2, 1. And the dimension of left null space. So the dimension of null space is n minus r, right? Neptune minus r. So the dimension of left null space, because we're just flipping, we're not doing anything else, we're just flipping, has to be m minus r. Mercury minus r. Of the dimension of the left null space equals m minus r. And you can see it, it's a one-dimensional space, but m in this case was, m is 2, m equals 2, n equals 3, r equals 1. M minus r is 2 minus 1 equals 1. Good. So the formula we had for the dimension of null space is the same formula for the dimension of left null space, but it's just the m's and n's have been exchanged. All right, so this is a subspace of 2 dimensions. Delicious. So what about it? These are the things that you cannot understand. Sort of. You'll understand them. These are the known unknowns. Or the known unmakables. Okay. Right. Right. Did I? Okay, I don't know. Okay. Okay. We've got it. So let's notice a few things. Okay, so let's draw this. So, am I going to say that now? Guess I could. Okay, so left null space equals a subspace of Rm, right, and contains all the vectors, contains all B that A cannot make. Cannot make, except for 0. All right. But that's just... So let's look at it. So column space for Inigo looked like this. We had y1, y2. We drew this before. So this is column space of, and I'll write it here, 1, 2, 2, 4, 1, 2. Yep. Column space is this character, and this is 1 and 2. This is a basis vector we found for it. We're happy with it. Right? Left null space is, very interestingly, at right angles. We notice that for null space and row space. What's our basis? It's -2 and then a 1. Right. So this vector in here, so this vector is, let me put it in here, this is 1, 2, and this is -2, 1. Wow. So this is column space. Right, we write it like this, and this is going to be, all this line here is null space. Yep. This is not quite right. So it contains B that okay. It contains B that A cannot make. I'll clarify this in a bit. To be clarified. Sort of misspoke there. So this line here, this is left null space. Left null space. And so we've written it as n, and it will be 1, 2, 1, 2, 4, 2. Like this, right? That's A transpose. So if we have any vector here, so A cannot make any vector here, right? And the thing that we start to figure out, they're at right angles, is that if we have a vector, and let's call this one B, we'll call it B, it can be made up of 2 parts because of this right angle business, and we'll get to this in the next, after the break actually. So P, we'll call it P for a reason, and we'll call this one E. So P is projection, and E is error. So this B we cannot make with A, right? We can't make it. We cannot make the E part, but we can make the B part, the P part, P for pirate, right? So A can make only P, only P, right? Which is the part of B in the column space of A. Okay, let me tell you more things. Oh boy, there's so much more to say. Okay, so let's add one more definition. I'll try to write up this fundamental theorem, and I'll give you a bigger drawing for this. And I think we have to work on this character after the break, but it will be a good example. Too much monologuing. So we need some definitions, some new definitions. So there's just some simple things. So we're going to say, all right, so we have one. And we have this in your heads already. But if x transpose y equals 0, and that's the same as y transpose x, right? Then we say x and y are orthogonal. It's just really a reminder, okay, just so it's there in your notes. And then 2, right, so these things are at right angles. This. If we have two subspaces, this is a bigger thing. If we have two subspaces, yeah. V and W, we say they are orthogonal, right? So the whole subspaces say orthogonal if if for every V in this capital V and W in capital W, right? Then the dot product of them in our matrix way is equal to 0. They're all at right angles. So here's an example, right? So every vector in here is orthogonal to every vector in here. So that's 2. And then 3, if the dimensions of V and W, and let's say they're in Rn, add to give n, right? And they're orthogonal, right? So if this follows on, they add to give n, then we say, and I'll write up here, we call V and W orthogonal complements. Complements of each other. And this is an important thing, so every x in Rn can be written as a sum of these, a sum of a vector from each one. Can be written as x equals V plus W. And V is in the big subspace here, and W is in this guy. Good. Right, so an example here is any vector, and it should be clear from this picture, from this one example. Any vector here can be written as some vector here plus some vector here. And you can think of the normal axes as doing the same thing. So we've shown that all vectors in null space are orthogonal to all vectors in row space. And, right? So, right. So, a good thing, right, is we've shown, right, so we've shown that well, let me, am I going to write this? Notation, notation, notation. Yes. We've shown that null space of A and the row space of A are orthogonal complements. We've already done that. They have this property. And the same thing goes for, because it's just a mirror story, same for the left null space and column space. Right, and the dimensions of these are R and M minus R. They add together. Dimension of this is N minus R and R. So they have this nice property. All right. Let me write down what we'll call the fundamental theorem of linear algebra. This is here. This is here. That. Yeah. Let me write this down. And then I want to draw up a big picture for the Inigo one. Okay, good. Okay. And then, if we can, tie it all to AX equals B. Okay. Madness. Put that there. Good. Okay. Cool. Cool. Okay. We're putting the fun in fundamental, as usual, fundamental theorem of. All right, I'll call it linear algebra. You can do whatever you want. Terrible naming. Linear algebra. Okay, so let's just write these things down. So the dimension of column space of A equals the dimension of the column space of A transpose equals R, rank of A, and A is an M by N. We've got that. The dimension of null space equals N minus R. The dimension of the null space, the left null space, is M minus R. Got those things. The dimensions add, so in fact we have that CA and the left null space are orthogonal complements. Complements in Rm, and the row space, so let me write column and row here. The row space and null space are orthogonal complements. Okay, and then we'll draw a picture. Draw a picture. Yes. N, that's good. Good. Got these things. And I think that's, yes. And then even better is the, okay. So there's this, and the bases we find for these things combine, right? So the bases for column space of A and left null space of A transpose combine to form a basis for Rm, and then we have the same things here, bases for row space and null space combine to form a basis for Rn for Neptune. Good. So there it is. We will add one more thing a long time from now. which is there is a special base. There are good bases. There's a very special basis. There's an awesome basis. We'll get there. All right, so let's try to draw this for yeah. Okay. Okay, so the big picture for Inigo, which equals 1, 2, 2, 4. So we have, right, we're going to end up over here, and we'll illustrate this problem. So it's a 2 by 3, yep, 2 by 3, right? So m equals 3, no, m equals 2, n equals 3, and r equals 1. There are pieces. Let's get these pieces back out. I'm going to put them over here. So we had a basis for, so here are the bases. So row space. Let me write it down like this. So row space was 1, 2, 1. That's it. Right? Do the reduced row echelon form here, we can just get 1, 2, 1. That's it. Column space itself, that has a basis 1, 2. We found it in a whole bunch of ways. That's one basis for it. That's fine. Left null space, we just found this one. And we found a basis -2, 1. And null space had a slightly bigger one, and it was, it has 2 in it. So it's -2, 1, 0, and -1, 0, 1. This is from before. Let's write down the dimensions. Dimensions, in general, just to say it again, r equals 1. R equals 1. This is n minus r, which equals 3 minus 1 equals 2. What have I done? This thing? That thing? Far right? Oh, this thing. Yeah, sorry. Yeah, M, Mercury, Neptune. The monks did fail us there. That was very bad. M minus R equals 2 minus 1 equals 1. Right, so dimensions column, good. Okay, let's bang it out. So we have 1, 2, 1. So this is a slightly painful thing because 3 dimensions. Ugh. Vizini, when we'll show you Vizini, will be a little bit better. So let's say this is x1, x2, x3. Right? So A sends x's over to y space, and that's a 2-dimensional thing. So here's y1 and y2. We've already gotten these pieces, so here's column space. We'll make it Kermit the Froggy. So this is column space of A. Right? 1, 2. Null space, left null space, left null space. Nice big right angles there. Very good. This is, this vector is, that's a -2, that's a 1. Right, so -2, 1. And this is a 1, 1, 2. I'm going to write it here. This is left null space. This is, right, done. Over here, we have to think a little bit. This is 1, 2, 1. That is the vector. So it's 1 out this way, 2 out this way, 1 out this way. So let's sort of draw it like this. This is going to be 1, 2, 1. And this goes on. And then I'm going to add what null space is. Null space is this plane, which is described by these vectors -2, 1, 0. Can I draw that? I need a white. I need white. Wow. So -2, 1, 0. So it's out this way. This way. Nope. -2. -2, 1, 0. So it's in that kind of direction. All right. So fine. So there's this one. That vector. This is going, we'll call it minus 2, 1, 0. And then minus 1, 0, 1. Yeah, it's not, in the, it's hard to draw, it's hard to draw, it's hard to draw, it's hard to draw. All right, so let's draw it out. It's hurting my brain. So I'm going to put it here. Okay, minus, this one here is minus 1, 0, 1. But there's a nice big plane here. This is null space of A itself. It's a 2D plane. And this is row space. So let's try to illustrate what happens. So we've got an X. Here's an X. It's going to have a piece in this plane, and it's going to have a piece. These guys are at right angles, right? Hard to see, but this plane is at right angles to this to row space. So we're going to have a piece here and a piece here. Let's draw like this, say. So this is going to be, this piece here is X particular, and this piece here is X homogeneous. It's messy. And X particular gets mapped over to here, somewhere in column space. A times X equals B. This part gets sent to 0. This is A times X homogeneous equals 0. We're going to draw more pictures like this, and the Vizzini one will be easier. But every X can be broken into two pieces, one that, depending on whether you have null space or not, one part that lives in null space, and we can, right? And then part that lives in row space. The row space one is the one that goes to the right place. So let me add that as well. So this one actually gets sent to the same thing. A times X particular equals B, if this is our B. This is out here, something out here. This was B. This is our E, and this is our P. This is unreachable. Right? So A cannot make anything off this line. Right? And I want to tell you one more thing before we go. Off CA. Cannot make anything more. Okay, what's going on? Row space is a one-dimensional line in 3 dimensions. Column space is a one-dimensional line in 2 dimensions. This matrix just loves this line here and loves this line here. And it sends this line to this line, and in principle could bring it back. So let's write that piece down. So let's say it. So A equals 1, 2, 2, 4, 1, 2 sends a line into, right, in R2, right? So the one that's given by 1, 2, 2, 1 is the basis, to a line in R3, sorry, this is R3, a line in R2, and here's the basis, it's 1, 2. Let's look at what it does, 1, 2, and this is the last thing. Right, so it's really just mapping a line, and it stretches it a little bit. So it takes this line and puts it over here and stretches it, and every other X, it just chops off the stuff that it doesn't understand. So it just chops off the part that's in null space. So let's do this, 1, 2, 1. This is a bit of a funny thing, but so this dot product's right, 1, 2, 1, so we're going to get 6 and 12, so that's 6 1, 2s. And if we think of, so what's the length of this vector? What is it? Square root of 6, right? So 1 squared plus 2 squared plus 1 squared. 1 squared plus 2 squared plus 1 squared equals the square root of 6. What's the length of this one? 1 squared plus 2 squared, we get a square root of 5 multiplied by 6. It's 6 times root 5. So, the growth factor, the stretch factor, let's call it stretch, and then we're finished. We're going to go stretch factor is 6 root 5 divided by square root of 6. That's a disaster. Square root of 6, which is the square root of 6 times the square root of 5, which is the square root of 30. So this matrix is basically just so this guy, 1, 2, 2, 4, 1, 2, is kind of equal to the square root of 30. It's taking a number, takes a number on this line, so you just give it a point on this line, multiply by the square root of 30, and then that's where it will be on this line. But everything else in this matrix tells you that this is the special line, and this is the special line. All right, we'll try again when we come back, and we'll make another one, and it will be just a 2 by 2. I know that hurt. It hurt me. That's why we don't do 4 dimensions. You too. Have fun. Have a great time. Only a couple hours every day on matrices. All right? That's all. That's all. Not too much. I mean, just limit what you, I know. Yeah. All right. Have a good break. Go ride bikes.